Hey, how are you, Professor Sahi?
Very well, very well. Oh, Joey, yes. Hi, hi. How are you?
All right, I'm good.
Okay, so I'm very glad to introduce Siddhartha Sahi from Rutgers University and announce his talk on a Stone-von Neumann equivalence for smooth representations.
Thank you, Dima, for a chance to speak in your seminar in front of friends. It's always a pleasure. Um, okay, so I'm going to report on some joint work in progress with Raul Gomez and Dima, and this sort of arose uh, from a problem in the course of our studying uh, Whittaker functionals. This notion of Whittaker functionals, um, generalized, degenerate. All kinds of Whittaker functionals which have some relevance to um, well, I mean, applications to automorphic forms, but also, as we've recently discovered, to mathematical physics. Okay, so what I'm going to talk about is something fairly general, and I have hoped to say a little bit about the applications to Whittaker functionals. Maybe I will just say a few words at the end, because yeah, because the rest of the talk is kind of pretty general, and okay, I would have to describe the whole setup for Whittaker functionals to be able to talk about the application. So I'll just kind of touch on it lightly at the end, explain how these things connect. Okay, so uh, let's see. So okay, how do I get rid of the? Oh, I can move it here. Okay, this is good. Let me resize this. So it's not, please bear with me for a moment. Okay, very good. So okay, so what we have done in this joint work is extend slightly the Stone-von Neumann theorem in a couple of different directions. So let me remind what it is. Of course, it should be familiar to many of you, if not all of you. So the Heisenberg group, which I will call H, or H sub n, is important in many areas of mathematics and physics, also analysis and so on. But okay, so it is the extension of a 2n dimensional vector space that I'm going to call W, or W sub 2n, by a one-dimensional center Z. So in this talk, I'm just going to talk about the real case. Anyway, that's where most of the new things or hard work is. So everything is real. Now, a fundamental result, which is due to Stone and von Neumann, a classic result, relates characters of the center to representations of H. More precisely, let's take a non-trivial unitary character of Z, chi, let's call it chi, this one-dimensional center. Then there is an irreducible unitary representation, rho equals the rho sub chi of H, which is unique up to unitary equivalence, in which Z acts by this non-trivial character chi. So that's the Stone-von Neumann theorem. And this result plays a central role in construction of the so-called oscillator representation of the metaplectic group associated to the symplectic vector space. And an important application of this oscillator representation is the theta correspondence for automatic forms. Sorry, if I sometimes start mumbling. Okay, so an important application is the oscillator correspondence for automorphic forms. Okay. Okay, so we're going to describe two generalizations of this result, and instead of just talking about irreducible unitary representations, we want to promote this to an equivalence of categories between suitable representations of H and of Z. So let me explain what this is. So the first is some algebraic generalization. This is given in Theorem A below, and it can be regarded as an extension of Kashiwara's lemma in the theory of D modules. Okay, I mean, it's a slight generalization, but it's not that much of an extension to the main idea. Okay, so the hard thing is the second generalization, which is given in Theorem B below, and this involves smooth representations, and so it is it's much more delicate, and it took a while. I won't go into all the technicalities, but they're pretty technical. So you can see them in the paper. Yeah. So I attended for many years Gelfand's seminar, and he would say that just explain the easy things. Don't try to explain hard things. It's much better if people figure them out on their own. So I'll try to explain the easy things, but maybe I'll say a little bit about the complexity. Okay. All right. So the point is that it involves fundamental ideas of Foucault-Ducloux and differentiable representations and smooth imprimitivity systems for Nash groups. Maybe I'll say a bit more about this in a bit. And what it allows us to do is to construct an oscillator representation for an arbitrary non-singular representation of the center Z. So it's functorial, so it's not about just unitary representations. Okay. All right, so let me explain first the algebraic result. Okay, so let's choose a maximally isotropic subspace L in W, or Lagrangian subspace. Then L, and in fact P equals L times Z, they are abelian subgroups of H. All right, so let me use fractal letters to denote the Lie algebras. And U of something for the enveloping algebras. Okay, and let me fix a generator, which I'll call little z, for this one-dimensional Lie algebra fractor Z. And now what does non-singular mean algebraically? So I'm going to write mz cross for the category of Z modules on which little z acts invertibly. That's what mz cross is. So, okay, I chose a generator, but evidently the category doesn't depend on the choice of Z, because all choices are okay up to scaling are the same. So this is the category, mz cross. So our algebraic result concerns the category which I call MLH cross. So these are non-singular representations of H, but there is an L that I'm carrying along here. So it consists of H modules which satisfy the following two conditions. So L acts locally nilpotently, and Z acts invertibly. So in other words, you have a locally nilpotent L action, and Z is acting, and the restriction to Z is an MZ cross. Okay, so that's the category. This category in the algebraic situation depends on the choice of Lagrangian L. And okay, so now what's the result? So if I'm given an H module M, I write M upper L for the subspace of L invariants, and then this subspace is of course Z stable. The subspace of L invariants is Z stable, and so the theorem is that this functor, which maps M to M upper L, is an equivalence from MLH cross to MZ cross. So it's an equivalence of categories. So how do we prove this? Well, we show this that by an explicit quasi-inverse functor. Namely, I take some n and I do the induction, the p induction to H. So here, E of n is just the trivial extension of a Z module to a P module. P is L plus Z. So that's all. Okay, so the key idea of this proof is the following lemma for a representation of the three-dimensional Heisenberg-Lie algebra. So we take a three-dimensional Heisenberg-Lie algebra with x bracket y equal to z, and then if you look at the kernel of x to the j plus 1 for any index j, well, that's simply obtained by repeatedly applying y at most j times to the kernel of x. So that's the main idea of the proof. I mean, I started by the assumption if x is something in L, then this kernel of j plus 1, the union of these kernels exhausts the module. That's the assumption, because L is acting locally nilpotently. Well, then this lemma tells you how to get everything from the kernel of x. And the kernel of x is precisely M super L. So this is how this lemma, well, okay, this is the three-dimensional case, but you can promote it once you know what's the main idea. So this allows you to prove this result. So you can get it by, yeah. Mm-hmm. So is that clear? If there's any questions. Okay. So now let me explain the analytic version.
Excuse me, I forgot to say I shared the link to the slides in the chat. So everyone who would like to scroll the slides in parallel is welcome to follow the link in the chat.
Oh, yeah, maybe you can share it again for people who join late. They don't always see.
So I just did. I just did. Okay. I think I also forgot to share it before, but now I did share it.
Mm-hmm. Okay.
Excuse me.
Yes.
What is your underlying field for all this?
So I said right at the beginning, I'm just working. Okay. So the ideas, I think, work in some generality, but I'm for the analytic stuff, I'm mostly talking about R because that's the hard case. Okay. That really is the hard case. That's where we.
I mean, the Stone-von Neumann theorem is stated only for R, as far as I know.
Well, okay.
The classical one.
Yes, the classical one, yes. But
Yeah.
okay.
Okay. Thank you. Thank you.
Very good. Okay, so let me explain the smooth version. Yeah. So I realized that I don't have a lot of slides prepared, so I can go as slowly as you want. I mean, I'm already more than halfway through the talk. But anyway, this is the hard part. So we give a smooth version of this theorem A, and okay. So now suppose G is a Nash group. So, for example, the Heisenberg group H or one of its subgroups P, L, and Z. For the application G, okay, for the application to Whittaker models or Whittaker functionals and so on, G could also be a real reductive group. But let's say that, that's also a Nash group. So let G be a Nash group. So then we write rep infinity G for the category of smooth nuclear Frechet representations of G of moderate growth. So if you have a Nash group, you can talk about representations of moderate growth. Okay, and let little z be a generator of the Lie algebra from the center as before. So what's a non-singular representation? So a non-singular representation of z, which I call rho m, in rep infinity z, is non-singular if it's invertible in the following sense, infinitesimally invertible. So in other words, I have a representation rho prime m in rep infinity z with the same m, such that the differentials are inverses of each other. So d rho z times d rho prime z is d rho prime z times d rho z equals 1. I should say 1 sub m. It's the identity on m. So, all right. So we write rep infinity z cross for the category of non-singular z representations, and rep infinity h cross for the category of h representations which are non-singular on z. So so I could just say non-singular representations of H. What I mean are just smooth nuclear Frechet representations of moderate growth, which are non-singular on Z.
May I ask a question?
Yes, please.
This condition about invertibility, is it different from just assuming d rho z is invertible? So you actually need a representation which composes?
That's right. We need to be able to integrate it also.
I see.
So therefore, it's better to say that.
So it's not automatic if you can just have one of. I mean, why can you not integrate without that weaker condition?
You need, in order to integrate that. I mean, so you need a bit more because not everything can be integrated. This is Hadi. Who's asking?
Yes.
Yeah. So we can discuss an example, Hadi, a bit later. But this is the correct formulation. So it's sort of an infinitesimal inverse within the class of representations that we are looking at. Okay. All right. So now, if I have a representation, I'll just say smooth smooth representation to mean all of those things. So I don't want to keep on nuclear fresh of moderate growth and so on. I want to keep on saying that. So if rho is some smooth representation, we can define the space of L co-invariants as the quotient M mod M1 bar, where M1 is rho LV. It's the span of rho LV minus V, where V is in M and L is in L. Yeah. So okay. So Dima assures me that this is already closed in the present situation, but I don't understand that completely. So I'll just put the closure of M1 for safety. I mean, it doesn't hurt. But anyway, that's the space of L co-invariants. And okay, so our theorem B is that this map from M to M sub L, that's an equivalence between non-singular representations of H and non-singular representations of Z. So it's an equivalence of categories.
That's essentially a Jacquet functor, right?
Say it again. Who's I can't see who's asking. Eyal?
Sorry, that's essentially a Jacquet functor, right? This MA.
It's a what functor? Sorry.
Jacquet functor.
Jacquet functor. Yes.
Yeah.
The Jacquet functor in this situation. Functor of co-invariance. Yeah. Right. But for the Heisenberg. Okay, so and it's an equivalence of categories between non-singular representations of H and of Z. Okay, so how do we prove this? Well, we prove it by showing that the following functor is a quasi-inverse, namely n goes to S ind E of n. So what are these things? Well, E of n is just the trivial extension of an n module to a p module. And S ind is what's called the Schwarz induction functor for Nash groups, which was defined by Foucault-Ducloux. Okay. Right. Okay, so as I said before, okay, so the proof of Theorem B involves ideas from the work of Foucault-Ducloux, but then we have to work a little bit hard to extend them. So the main point is to, so if you just go back to the theorem, it says that this is kind of the inverse functor. So in other words, if I mean, what's involved in proving this is a sort of a recognition theorem, that you have some representation and you want to show that it is induced from something. In order to show, so say that you can come back to it, you have to recognize it as being induced. So in the algebraic case, this was what this little lemma kind of accomplishes. But here, in order to prove that something is induced, the idea in Mackey theory is that you construct a system of imprimitivity. And well, so it gets a little bit more technical because representations aren't irreducible. We're not talking about irreducible representations. Nevertheless, so one has a notion of system of imprimitivity. So all right, fine, it's induced not from something irreducible, but from something more general. And one can, for representations of Z, which is just one-dimensional, you can try to construct systems of imprimitivity using in some geometric way, and So you can use the Fourier transform to help out. So this is those are sort of the tools, but it's a little bit complicated. You can see it in our paper. So okay, so I want to emphasize, this is some remarks in Theorem B. So I reiterate that Theorem B is using co-invariance rather than invariance. And what this means is that we're using homology rather than cohomology. So in the infinitesimal situation, the result was using about cohomology. Now this is about homology. And the advantage is that this leads to a better result, because the representation categories don't depend on the choice of Lagrangian. So the algebraic result had somewhat broken symmetry, because I chose a Lagrangian to define the category. Well, now I'm not. So, and in fact, so what happens is we get a family of equivalences between the same two categories, depending on the choice of Lagrangian. Of course, the functors we write down depend on the Lagrangian, but the categories themselves don't. And this plays a key role in the next result. Okay, so oops, I don't know how to spell symplectic. Okay, but anyway, I just want to reiterate that the Heisenberg group, it's an extension of a symplectic vector space by a one-dimensional center Z. And so thus, the symplectic group acts on H by automorphisms, fixing Z. And now suppose if I have an irreducible unitary representation of H with non-trivial central character under Z, then by the Stone-von Neumann theorem, rho extends to a representation of the universal cover of the symplectic group. So this is what the Stone-von Neumann theorem gives you for free. And okay, so the result of the Siegel-Schale way is that this extension descends to a double cover of the symplectic group, which is called a metaplectic group. Okay, so I just recall the definition of the metaplectic group. And so our final result is a smooth analog of this theorem. And here it is. So any non-singular representation of H extends to a representation of the metaplectic group. So these are, of course, the representations of the metaplectic group you get are not new, but this result, I mean, the point of this result is that it's functorial and geometric. And so this is some tool that we need for our work on degenerate Whittaker functionals, but because the Heisenberg group is kind of so ubiquitous, I guess we would like to think that it might have applications in other areas as well. Okay, so I mean, this is all the slides that I have. Let me maybe say a few words about the application. Well, we're still kind of working on that a little bit, so I don't want to put it in writing yet. But the main point is that in our work, we discovered with Dima and Raoul, we discovered that one should look at a more general class of Whittaker functionals, which depend on a pair, some semi-simple element and some nilpotent element, which follow which behave like the Borel in SL2. And what's kind of important is to understand how this semi-simple element defines a nilpotent Lie algebra with a Heisenberg quotient, and this nilpotent element defines something like the oscillator representation of this Heisenberg Lie algebra. And it's important to understand how the space of functional depends on this semi-simple element. And we have some method for tracking how the space changes. Now, what one would like to say, one would like to have is a tight relation between the space of functionals. Okay, one would like to show that something is actually independent of this semi-simple element. Some space of functionals is independent of this semi-simple element. And for at least for maximal nilpotents for the representation. And so for this, apparently it's true not at the level of functionals, but equivariant functionals, but for generalized equivariant functionals. But to define the correct notion of generalized equivariant functionals, one needs to have some independence of polarization of the sort of thing that one has for something along the lines of Theorem B. So Theorem B is what's useful for defining this notion of generalized generalized equivariant Whittaker functionals, which we're temporarily calling pro-Whittaker functionals, and there one can prove an independence of the semi-simple element. We hope so. That's what's going to be the application. Okay, but as I said, the result, the Heisenberg group is the Heisenberg group. Okay. So I think that's really all I have to say.
Okay, thank you very much. Questions, please.
Is there any? I mean, this is an existent. This is an extension theorem. Is there some? I mean, it cannot be unique, but is there some sort of? I mean, characterizing these extensions, or it's just the existence theorem? That's.
So I mean, so it's like a functor, if you. I mean, it's one can ask rather than uniqueness, because it's about categories, right?
Yeah.
So
yeah.
We actually have a functor, and we can investigate properties of the functor.
Okay. What is it? Do you know the? I mean, is the functor? I mean, explicit enough that you get information about it, or?
Yeah, I mean, so the oscillator representations aren't new. The point is that they're gluing together in the same way.
Okay.
So representation of Z is some, it's kind of arbitrary.
Okay.
Except it's smooth and non-degenerate. No irreducibility assumed at all. And this is, I mean, the reason it's useful is typically when you restrict from something large. So you have a reasonable representation of a large group. And after you restrict it, it's not that reasonable.
I wasn't expecting any uniqueness. I was expecting a characterization. That's
okay. So Fredwin, we will think about it. I can say. So we'll try to see if we can nail it down a bit more.
Okay. Thank you.
Sure.
Is there a p-adic analog of this, or complex? Or the complex case is not interesting, but
complex case. We didn't. Guess we didn't explicitly think about the complex case there. Of course. We didn't think about it. I mean, there, of course, maybe we should just get the symplectic group rather than the metaplectic group. Okay, but we didn't think about it directly.
So do you know anything about the indecomposable elements in this rep infinity Z star? Somehow the basis, the source of everything here is rep infinity Z star, right? In other words, that's everything's coming from that And so, of course, for those of us who do the sort of classical world, we have an irreducible character, your chi that you took at the beginning. So, and a unitary one. Can you draw for us or explain for us some examples of things that come up in your larger category here that are maybe, say, lead to indecomposables, or in others? I don't want to just a direct sum of chi's, right? And I don't want to just maybe, of course, what you're saying is that, for example, you could take chi to not be unitary by putting some absolute value to some power s in it or something like that. I mean, I suppose that's also included in your game. Yes. So what are the new representations of on rep infinity of Z star look like?
So there is a mother representation. So now we're
yeah, okay.
let me see if I can. Let me see if I can. Oops. So it's just. I think you can look at the kind of. So you can look at the Schwarz. Just look at the algebra of Schwarz functions on Z.
Mm-hmm.
Right, and it's really the Schwarz functions on the real line, but on I think on Z cross.
Mm-hmm. On Z cross.
On R cross.
R cross, yeah, okay. Mm-hmm.
Yeah, Schwarz functions on R cross, and this is an example of So there's a notion of so here's a characterization of non-singular representations of Z. So so you look at so you look at Z hat cross. So in fact, let me say the following. So you look at Z hat, so the dual group Z hat, and you look at Z hat cross. In other words, you throw away the trivial representation, and then you look at the Schwarz functions on Z hat cross. So a non-singular representation of Z is the same thing. Okay, this is a Frechet algebra, and a non-singular representation of Z is the same thing as a differentiable S Z hat cross module.
I see. So there's a sort of a Fourier transform involved here.
Exactly.
Right. Okay. I see.
So let me add a little bit that irreducible representations are just unitary characters. For unipotent groups, the moderate growth condition, which is one of the technical conditions that Siddhartha didn't spend your time on announcing, forces it to be unitary. That's because the group is unipotent. For reductive groups, every character is moderate growth, but for this, it has to be unitary. But in the composable ones, one possible is you can glue two trivial representations together to form two-dimensional in the composable representation.
Yeah. With a logarithm in the upper corner.
Absolutely.
You have some logarithm. So there's some unipotent part where you get some logarithms and so on in the upper triangular part.
Yes.
Yeah. Okay.
Yes.
Okay.
Yes.
Okay.
And this is a quotient of this mother representation that Siddhartha talks about by x squared.
I see.
Yeah.
Well, we don't consider the trivial representation, so it should be something like x minus I squared.
Yeah.
Yeah. Okay. Yeah. I see. That's the non-singularity condition.
Yes.
Right.
Yes.
I see. Right. Okay. I was just curious because these are. I mean, you want to see what do we buy? What do we buy with this?
Exactly. Yeah. So right, I should have maybe explained a bit more, but well, maybe I just mumbled about why we are doing this.
No, you let me ask a question. That's the point. It's great.
Right. But yes, I guess certainly you want to know what else can you do. So that's a good question.
Excuse me, how do you recover the classical Stone-von Neumann theorem from your Theorem C?
Classical Stone-von Neumann theorem. Theorem C is not the Stone-von Neumann theorem. Theorem B is maybe a generalization of the Stone-von Neumann theorem. Theorem C is a generalization of the Siegel-Schale-Way theorem. Theorem B is, I think. So who's asking this question? I don't see who's asking this question.
No, I'm Sengupta from TI. Yeah, well,
sorry, I missed that. What? Sorry.
No, so what was your Theorem B? It has gone back so much.
Can you see Theorem B? Am I sharing it?
No, I can't see on the screen. It is
I stopped sharing.
Yeah.
Yes, you started sharing something else.
Oh, I started sharing something.
Yeah, this is some other file. The paper maybe actually.
Okay, I started sharing. Oh, okay. Let me share again. Where did I? Oh, now I closed it. Am I sharing it now?
Not yet.
Not yet. Okay. Now I lost. Sorry, I'm not good at this at all. Okay, let me share the screen. And I share this. Share. Okay, is that sharing now?
Yes.
Oh, good. Okay, let me go to full screen mode. Yes. Yeah. So if you have an irreducible unitary representation of Z,
you're not sharing.
Not sharing. The screen is blank.
Sharing.
You're sharing a line.
Yeah. White line.
Oh dear. Resume share. Okay, good. How about now? Okay. Sorry. Yes. So So if so, this is some equivalence, but
thank you. So this is the right generalization of the Stone-von Neumann theorem.
Yes, that's right.
That was unitary. You're replacing non-singular, smooth, and all that.
Yeah, exactly. And it's about categories rather than just.
Okay, fine. So your Theorem C is a new result. It's not. It's a generalization of the Siegel-Schale-Weil representation.
Construction, yes.
But why does the semi-direct product with H come in? Can you just tell in a line?
No, that's what the extension is, even in the Siegel-Schale.
This is the novelty of your result?
No. I mean, the Siegel-Schale-Way theorem.
No, I'm saying that is just the representation of the metaplectic group, right?
Yes.
So we don't need to have semi-direct product with H there in the statement. But here you have one.
So I'm not sure. Maybe I should have said that the Siegel-Schale-Way says that, the extension is a representation of the semi-direct product.
Oh, of the semi-direct product. Oh.
Yeah, because it's already a representation of rho and.
No, you can do it, but I'm saying as such it is stated only for the metaplectic group.
Yeah, but it could be stated.
Point,
It's not a big
deal. Okay, thank you.
You're welcome.
So I wanted to ask regarding Theorem B.
Yeah.
So there are some other generalizations of the Stone-von Neumann result for covering groups, and I was wondering your technique, your proof technique is probably very special to the symplectic group, right?
Oh, well, no. So I mean, it's not that we wanted to do the symplectic group. It's just that that's okay. So we're really interested in the Heisenberg group because that's what shows up in the study of degenerate Whittaker models. That's really where the action is. So And so then, okay, and then it leads us to the symplectic group. Now, can this technique be extended for other nilpotent groups or unipotent groups? Probably, but we didn't kind of do that. So it's certainly if you want to do something along those lines, that's fine. So the Heisenberg group is. I remember that sorry, this is just like it's still being recorded, or we stopped recording?
Yeah.